There's this creative technique that shows up all the time in many of the big proofs in mathematics called the determinant trick. Let's see how it's used to prove Nakayama's lemma, which is one of the foundational results of commutative algebra. So the setting is the following. Suppose we have M, a finitely generated A module, where A is a commutative ring. Suppose we have an ideal I in A, which is also in the Jacobson radical of A. Now the Jacobson radical of A is just the intersection of all the maximal ideals of A. Nakayama's lemma now states that if we have Im equals M, this implies that M equals 0. So it's a test to determine whether the module M is trivial. Now the proof starts as follows. We have that M is finitely generated, so we can find a generating set of M. And we know that since M equals Im, we have that all Mi's can actually be expressed as a combination of the other generating elements with coefficients in I. Right? So we can actually re-express this using linear algebra as a vector equality, where S here is just an n by n matrix given by these aij's. Right? So the elements are in I. Okay, so this vector inequality can be rewritten like this. And if we compose both sides with the adjugate matrix of the identity minus S, we have now this equality here. And the determinant trick starts by recognizing that this element here, or that this term here, is actually equal to the determinant of the identity minus S times the identity. Right, so now we have then this equality, which is equivalent to this if we look at each term, right? So we have this for all i's. Now, if we can prove that the determinant of the identity minus x or minus s is invertible in A, then we're done, since we can just take this equality here and multiply both sides by the inverse of this determinant, right? And then on the left-hand side, we'll have this canceling out to 1, and on the right-hand side, we'll maintain the 0. So we'll have each mi equals 0, which will imply that our module M is trivial. Right. So note that the utility of the determinant trick was really exchanging a problem about modules, right, the module M, for a problem regarding the ring A. Okay, so all we need to do now is show that this determinant is invertible in A, and we'll be working now in the quotient A over the Jacobson radical of A. So using a few calculations involving the equivalence classes within this set here, we have that the equivalence class of 1 minus the determinant of this guy here is equal to the equivalence class of 0, right? Therefore, 1 minus this determinant is in the Jacobson radical of A. And I'll leave it as an exercise to show that the Jacobson radical of A can be equivalently defined using what's in this blue box here. And using what's in this blue box, if we take y equals 1 and x equals 1 minus this determinant, then we immediately have what we wanted, that this is invertible in A. And we're finished.